Okay, so in chapter 10, we are talking about gases. So in chapter 8, we talk about aqueous solutions, and in chapter 10, now we're switching gears to talk about gases. So first, let's talk about 4 variables that affect gases, and then we'll get into some formulas that we'll use to look at the relationships between these different variables. So the 4 variables that we're going to talk about that impact gases are pressure, volume, temperature, and amount of gas. Okay, so pressure of a gas. There are multiple units that you're going to see used when we're talking about pressure. And there are tables in your textbook and on the PowerPoint slide that show you how to convert from one unit to another. There are certain times where you will need to use one unit, so you'll have to convert from one to another. And then there are certain times where it doesn't matter which unit you choose to report your answer in. Some of the units that we're going to see are atmospheres, which is abbreviated ATM. Another one that we'll see is something called millimeters of mercury. And then there's something called a torr. And then there are pascals and kilopascals. So these are all different units that represent the amount of pressure of a gas. We will probably talk about atmospheres most in this class. Millimeters of mercury is usually something that you see in meteorology and weather, or inches of mercury when they're talking about atmospheric pressure. Pascals, kilopascals, torr, these are sometimes used more in physics. But you'll have a chart that will allow you to convert between any of these pressures, depending on what the problem gives you. The next unit, volume, the variable for volume that we will mostly use is liters. You might see some volumes in milliliters, and again, there will be certain situations where you can use any volume, and then certain situations where it has to be in a specific unit, and I'll make sure to mention that. Temperature in chemistry almost always needs to be in units of Kelvin, and oftentimes you're not given the temperature in Kelvin. You might be given it in degrees Fahrenheit or degrees Celsius. Just pay attention to the times that a unit needs to be Kelvin and that you're converting it from Fahrenheit or Celsius. Amount of gas will need to be in a unit of moles. Sometimes you're not given the moles of gas, you're given grams, or you would even be given volume. And then you would need to convert from grams or volume into moles. The variable that we use for number of moles is N. So when you see N in a formula, it's referring to the number of moles of gas in this case. Temperature is capital T, volume is capital V, and pressure is capital P. So we're going to use all of these. We're going to look at some of the relationships between these variables individually, and then we're going to put them all together. So the first law that we'll look at is called Boyles Law. Today we'll look at Boyles Law, Charles' Law, and then something called the combined gas law. You don't need to know the names of the laws. You just need to know how the formulas are used and which is which, but I wouldn't ask you a specific question about the name of the law. So let's look at Boyles' Law first. So Boyles' Law is looking at the relationship between pressure and volume. So pressure and volume are inversely related. What that means is if one goes up, the other goes down. Pressure of a gas is inversely related to volume of a gas. Inversely related. So that means if pressure goes up, volume will go down. Or if pressure goes down, volume will go up. So a lot of times when we're talking about gases and you can think of a real example, that's always helpful. Think of a balloon. If you have a balloon and it is at a certain pressure and volume and you squeeze that balloon, if you squeeze the balloon, what you've done is you've decreased the volume. You've decreased the size of that balloon, and what that does is it increases the pressure. So anytime you can relate what we're talking about here with some real life example, that's always helpful. So let's look at an example. For Boyles Law, we can use any unit, of pressure, any unit of volume. So we probably would just use whatever units are given to us in the problem. So this problem says, I'll just write it out for us. A volume of oxygen gas occupies 38.7 milliliters of space at 751 millimeters of mercury. So this is the volume and this is the pressure. What is the volume if the pressure changes to 359 millimeters of mercury? Okay, so the formula that we use for Boyles Law is this. It says P1V1 equals P2V2, where again 1 and 2 represent initial and final conditions. So we're going to look through here. We're going to be given 3 of these 4 things. We're just solving for the 4th. So it says a volume of oxygen gas, especially remember now that we're in the gas chapter, to pay attention to the diatomic molecules. Those are all gases. So remember the diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. I'll post those, but you need to remember that those diatomic molecules that are gases all exist. So oxygen is O2. It's not just O. That's going to be really important later when we start doing calculations and things like that. So that's a good thing to have near you when you're doing these problems. So a volume of oxygen occupies 38.7 milliliters of, that's the pressure. So the volume is 38.7 milliliters, and the pressure, this should say at, not of. Volume of gas occupies 38.7 milliliters at 751 milliliters of mercury. So this right here, this is my V1, and this is my P1, and this, it says what is the volume, what is V2, if the pressure changes to 359, P2. So now we're just solving for V2. So I'm going to say 759 millimeters of mercury times 38.7 milliliters equals P2, 359 millimeters of mercury times V2, which is what I'm solving for. So I'm just going to divide both sides by 359 millimeters of mercury. Millimeters of mercury will cancel. Your answer to V2 is going to be in a unit of milliliters. Your answer should have 3 significant figures because all of the numbers in your problem have 3 significant figures. You should get 81.0 milliliters. That's the final volume. So let's think about if this makes sense, because what we just said is that the volume of the gas was 38.7 at a pressure of 751 millimeters of mercury. The pressure is decreasing. So I just said if pressure decreases, that means volume should increase. And 81 is a bigger number than 38.7. So this number does make sense. So that's Boyles Law. Boyles Law looks at the relationship between pressure and volume. So let's look at another one. Let's look at something called Charles's Law. So Charles' Law looks at the relationship between volume and temperature. So I'm going to say volume of a gas is directly related to temperature of a gas. So volume and temperature are directly related. So what that means is if volume goes up, temperature goes up, or if temperature goes up, volume goes up. So again, this is true if you think of the balloon example. If temperature going up isn't something that we see all the time, but what is pretty evident is if you've ever had a balloon in your car, or maybe just a water bottle or something, and it had air in it, and some sort of gas, and then you left it in your car overnight, and it was cold. The next morning when you went out there, that balloon would be deflated because the temperature decreased, so that means the volume decreased. So these are directly related. So if temperature decreases, that means volume will decrease. Or if temperature increases, that means volume will increase. This is also true, it's a little less direct, but if you've ever left soda in your car on a hot day, the carbonation, which is gas, the carbonation in that bottle, when you open it, is going to try to get out of that bottle really quickly because the volume of that gas is now taking up more space. So when the temperature increases, the volume increases. So same thing, but the formula now looks like this. V1 over T1 equals V2 over T2. So notice the difference in the way the formula looks if something is inversely related versus if something is directly related. So let's look at an example. So this says you prepare carbon dioxide. I'm just going to write it over here. You prepare carbon dioxide, CO2, by adding HCl, hydrochloric acid, to marble chips, which is calcium carbonate. According to your calculations, you should obtain 79.4 milliliters of CO2 at 0 degrees Celsius. How many milliliters of gas would you obtain at 27 degrees Celsius? Okay, so one important thing about Charles' law is that the unit of temperature does matter. The unit of volume doesn't matter, but the unit of temperature does matter. So for Charles' law, temperature must be in Kelvin. So in this problem, they give us 0 degrees Celsius, 27 degrees Celsius. We're going to need to convert that to Kelvin before we can use this equation. But the same thing, we are given V1, we are given T1, which we need to convert, and we are given T2. So we're solving for V2. How many milliliters of carbon dioxide? Milliliters of carbon dioxide would be V2. So let's see. I'm going to convert 0 to Kelvin by adding 273. So degrees Celsius plus 273 equals Kelvin. There's no degrees Kelvin, it's just Kelvin. So I'm going to write V1, 79.4 milliliters, over T1, which is 0 plus 273, 273 Kelvin, equals V2, which is what I'm solving for, over T2, which is 27 degrees Celsius plus 273, so that's going to be 300 Kelvin. Now I'm just going to solve for V2. So I'm going to multiply both sides by 300. Well, I'm going to cross multiply to solve for V2. And when you do that, you should get a V2 because units of Kelvin will cancel. Your unit of volume will be milliliters. Again, with 3 significant figures, because you're going off the number of significant figures in the temperatures, and then the volume here, like this has no significant figures, so you wouldn't go off of these temperatures because you're using temperatures in Kelvin, not temperatures in Celsius in your equation. So we're going to have about 87.3 milliliters. And let's think about if this makes sense. So if I have 79.4 milliliters of gas at 0 degrees Celsius and I'm increasing the temperature, that means the volume had better increase. So this is, again, just a good check for you to know if you are solving a problem correctly.